Hello AP Calculus AB students, Mr. Record here. We are looking at video number 5. This is example 5 from our topic 4.2 over straight line motion. And I'd have to say that this is probably my favorite example. It really uses so many of the ideas that we have discussed thus far and packs them into one really nice, robust, free response question that will really help you guys understand the key concepts that are so vital to straight line motion. And a lot of these same ideas will show up on the AP Calculus exam. So, like I said, I'm very excited about this problem. Kudos go out to my good friend Brian Passwater authoring this question. He's a great calculus teacher at Speedway High School. And without further ado, let's take a look at our example 5. Notice that you have a table with a lot of information. And as I read through, it says for time intervals 0 to 8 seconds, a particle P moves along the x-axis. The position, velocity, and acceleration of particle P are all differentiable and modeled by the functions x of p, v of p, and a of p, respectively. Selected values for x of p, v of p, and a of p are shown in the table where x of p is going to be measured in meters. So basically we've got a table with 4 different times and we can tell exactly what the position, the velocity, and the acceleration are at those times. I know we don't make a big reference to the fact that time is measured in seconds, but it was mentioned in the problem. Now, lots of different things can be asked and fashioned together from this information. And so we're just going to take these one at a time, starting with part A. Is particle P moving towards or away from the origin at time 4? And you have to give a reason for your answer. Now, there may be more than one way to depict the reasoning for why this is going to be true or not true. So one of the things that I like to do is establish position first. So to establish the position of particle P, we know that x is the position. And we will use, and I'll tell you what, let me switch to a blue. And we'll use the subscript P, so we're dealing with particle P. And I know you might be thinking, why? Is there a different particle? Wait, there's a new one that's coming down the pike here in a bit. And if I figure out what's happening at time 4, well, all I've got to do here is read from the table, and I can find that that particle as it is at position 6. So if we have an x-axis, think about where 6 is. That's where that particle is at time 4. However, that's not telling us if we're moving to or away from the origin. We're going to have to figure out what particle P's velocity is. Well, the velocity of particle P, or v sub p at time 4, can be read from the table, and that gives us a -1, of course. Now what you would have to do is understand that a negative velocity means that the particle is moving to the left. And if you're at 6 and you're moving left, you're going towards the origin. So basically, write it up and say the particle at time 4, and you could write this a variety of ways. A particle at time t equal 4 is located at x equals 6. And couple that with the particle's velocity at time 4 is negative. That would likely be enough, but if you want to add a little bit more, and is therefore moving left. Like I said, you don't have to be quite as robust in your explanation as I am, but I know that this is going to certainly count and award all the points. Now, we need to make sure that we answer the question because I haven't answered the question. And therefore, we can say, so the particle is moving towards the origin. And if you're writing this, if you have the notes and you're writing this, of course, you might want to pause the video if I'm going too fast. But that is a splendid reasoning as to why this particle is moving towards the origin. Establish that it has a positive position and a negative acceleration, and that all the puzzle pieces come together there. All right, let's take a look at part B here. It says, is the particle P speeding up or slowing down at time 7? Again, give a reason for your answer. Well, fortunately, if you've watched one of our previous videos that led up to this example 5, I think you may have seen a couple of instances where that question has been addressed. And all you've got to do is compare the signs of the velocity and the acceleration. And we have that information in our table. So you're going to find the velocity of particle P at time 7. Reading that from the table, we get -4. And let's find the acceleration of particle P at time 7. Reading from the table, we get -3. Now just remember, if the two signs are the same, that means they're working in tandem. We are moving to the left and we're being pulled farther to the left because this acceleration force, and therefore that's going to cause us to speed up. So you want to say the particle is speeding up. So you've now answered the question. Now you got to give me a reason. And so I think the best way to say this is we're speeding up at t equals 7 because v of p of 7 and a sub p of 7. And I think you could say have the same sign because you have the proof over here. You could go ahead and repeat what the two values are. One is -4 and one is -3 and have the same sign. You could do this a variety of ways. I'm going to try to use the fewest words as I can because part A was a little bit wordy. And because I can see that these have the values over here, I'm just going to say because A and V have the same sign. I think that's a little bit better argument than if you said they're both negative. Because if you say that they're both negative, that could mean that, well, that's the only instance when we have a situation where the particle's speeding up. Well, no, that's not true because if these were both positive, we would also be speeding up. So that's why I like to say they have the same sign. And boom, there's your proof right there. Okay, moving along, we're going to take a look at part C. Part C says, use the data in the table to approximate V sub P of 2, indicate the units of measure. So again, if you're following along with my curriculum, this kind of goes back to topic 4.1, way at the very beginning of this unit. So to approximate V sub P of 2, you have to know that we're going to have to use a difference quotient. We're going to have to understand what is the definition of velocity, and that is the change in position over the change in time. Now, if you look in your table, the 2 is not present as a time value, but it just so conveniently seems to be sandwiched nice and evenly between 1 and 3. So for that reason, we can use the positions at time 3 and the position at time 1 and subtract and make our difference quotient. You don't have to say approximately. It's very good that you do because this would be an approximation given the data that we are provided. Once you write a difference quotient, it's likely that you could earn a point on the AP exam. You would not receive full credit until you extract the values from the table, which in this case, I would have 8 minus 2 over 2. And if you want to go ahead and simplify this, this would become a 3. Now, this would not earn the full credit for the answer until I put the units of measure. And because the position is measured in meters and the time is measured in seconds, I have meters per second. And that's all that you've got to do for part C. Moving along to part D. Is there a time C where C is lying between 1 and 7 exclusively, meaning we don't include the endpoints, such that V sub P at time t is equal to 0? Justify your answer. Well, this is going to go back to a concept way at the beginning of the course. It's way at the beginning of when we were talking about Unit 1. I believe that this is topic 16 in Unit 1, dealing with the intermediate value theorem. So this is a bit of a curveball if you're my students, because we kind of sporadically talk about this, so you want to pay real close attention. Basically, what you want to do is you want to determine what's happening, let's say, somewhere along this interval 1 to 7. So, for instance, we could look at time 1, and we could look at time 7, and we could look at the V value and see that, well, you know what, guys? The V value there and the V value there are 5 and -4 respectively, which looks like we got a positive and a negative, right? Well, if you have a positive and a negative value, and you know that the function that joins those two is a continuous function, then we have to cross 0. We have to have a value of 0. You can't get from 5 to -4 without being 0 at some point. Now, the thing about this problem that might bother students is the fact that this is presented on an open interval. The reason for that has a lot to do with the differentiability aspect, and I don't want to get into that. It's not really important. So what you could do is say, well, what if I looked at a sub-interval between 1 and 7? In other words, what if I looked at what was happening on the interval 3 to 4? Do you still have that same relationship between a positive and a negative V value? And the answer is yes. So what we could do is we could say that, yes, this is definitely true. And if you want to be even more thorough, you could say, yes, because of the intermediate value theorem. And I'm just going to abbreviate that. Now, you do not have to mention the theorem by name. That's not a requirement. But you do have to talk about the conditions of the theorem and what the theorem is saying. So I might want to point out that the interval 3 to 4, the interval 3 comma 4, is a part of the interval 1 to 7. So we start there. Okay, well, that establishes the fact that we can use 3 and 4. Now we need to say that V sub P of t is differentiable. Now, what does that mean? If we're differentiable, that means that we are also continuous. And that's going to be very important. That is something that must be stated. If we don't establish the fact that this function V sub p is continuous, we're not allowed to use really any theorem throughout AP Calculus. And so often on the AP exam, students have to write this statement. It's very, very common. It used to be the fact that we could just say that the function's differentiable and continuous, but on a recent problem on the AP exam, it was very important that the student use the word therefore to establish a causal relationship. So I'd like to instill that into both my students and anybody else that's watching this video, because it could be very important. Now what we're going to do is establish what the values of V are at 3 and 4. So we can say that V sub P of 3 is equal to positive 2 from the table, and V at 4 is -1. And now the ball is rolling. Now what we can do is we can say, well, because 0 lies between 2 and -1, then we know that the IVT is going to work. And we could just simply say that V sub P at 3 is, actually, I might want to turn this around. Let's start at 4. So I'll say that the value at 4 is less than 0, which is less than the value at 3. And all of those pieces really come into play to say, therefore, at some C, right? And I think we used the times C. V sub P at C must equal 0. And this is maybe a little overkill with the explanation, but why not? Why not set the bar really high? It really doesn't matter what order you have these arguments presented. Maybe you start off with the differentiability implies continuity. Maybe you start off with where the values of 4 and 3 happen to be. As long as you relate to all of these things, you're going to get full credit. And the best thing of all, at no point did you have to say the intermediate value theorem. If you fail to mention intermediate value theorem, it's okay. Just be careful. You don't want to use a different theorem that doesn't apply, because that could possibly cost you. All right, let's take a look at our last example part, our last part of this example. It says here in part E, for interval 5 to 8, a second particle, Q, comes along the x-axis here and starts moving. The position of particle Q is modeled by this particular function. And at time 7, we're asking, are particles P and Q moving toward or away each other? And of course, we're going to have to explain our reasoning. Well, anytime that you're establishing whether particles move towards or away, you're going to have to know where they are. And where they are is a matter of finding position. So we're going to find the position of particle P at time 7. And that is read from the table. And we see that that's equal to 5. You want to do the exact same thing with particle Q at time 7. Now this one might take a little bit more effort because you're going to have to actually plug in 7 into this position expression. And doing so, we'd have 12 minus negative 3 squared is positive 9, and therefore we get 3. Okay, now what's happening here? Well, if I have a number line and I know that here's 3 and here's 5, all I know is that particle P is right here and particle Q is right there at time 7. But that doesn't tell me how they're moving. In order to establish if they're moving towards or away from each other, I'm going to have to figure out what their directions are. And the direction of these particles is found by looking at velocity again. So we're going to figure out, well, what is the velocity of particle P at time 7? Well, we go to the table. Particle P at time 7 has a velocity of negative 4, which means P is moving left. Okay, is moving left at time 7. Well, that's wonderful because I know that this particle P is doing this. Oh, he's getting closer to Q, but I don't know what Q's doing. Maybe Q's running away from P. Maybe Q doesn't like P. So we're going to have to figure out what is the velocity of our good friend particle Q at time 7. Now to do that, we're going to have to know what the derivative is of our particle. So I haven't taken this derivative yet, so I'm going to work that right here. I'm going to say x prime of q, sub q at t, which is the same as the velocity. Let me move this guy over a little bit so I got a little bit more room to work here. So I've got x prime sub p is v sub p. And I know sometimes these variables can get really confusing. Don't let that be a thing. I like these subscripts because it tells me which particle I'm dealing with. Is it a p or is it a q? X still means the position, v still means the velocity. So if I take this derivative, the derivative of 12, of course, is 0. And then if I differentiate this piece right here, the 2 would come out in front. I still have the negative there. And then I have t minus 10 to the first power. And technically, I would use the chain rule, but the chain rule derivative of t minus 10 is just a 1. So there's my velocity. So if I want to figure out what is the velocity at time 7, I just merely need to plug 7 in for that t. And this, of course, will give me negative 2 times negative 3, which is a positive 6, which means q is moving right or to the right at time 7. And I want to say we have now determined what's happening. I can't make both particles move simultaneously. I don't have that freedom here. But if P moves left and if Q moves right, then they're certainly moving towards each other. And so we have established the argument. I'd say we've explained it very well. Now we just tie it up and say, therefore, particles P and Q, or you could probably say the particles, are moving towards each other. And you really don't have to say much else. I would probably mention the time because that may not be true all the time. The information is there. The explanation is there. There's no need for you to verbalize the findings that you've already put together. Pretty robust problem. Like I said, it's one of my favorites because so many things are jam-packed into this. This is a great problem to study as you're preparing for a quiz or a test because it contains so many of the elements essential to particle motion. I hope this helps, and we'll see you at the next video.